All right. Going ahead, get started with this. Um, Today is an advisory day, so we get out 10 minutes earlier, I think. So just be aware of that. That class schedule a little off. Advisories after second. All right. So looking at this, chlorine. What would you classify that? Pure or mixture? All right. So it definitely is pure. All right. Element or compound? Element. Even though it's Cl2, it's still an element because it's only chlorine. All right. Water. Pure or mixture? Pure. And then it's a compound. All right. So remember that the only two things that can be considered pure is if it's an element or a compound. All right. Rocky Road ice cream. Mixture. All right. Heterogeneous or homogeneous? Hetero. You can see the different things in it. The chocolate chunks, the marshmallows, the ice cream. All right. Sugar water. So it is a mixture. Now, when you look at sugar water, are you going to see the sugar in the water, or are you just going to see one substance? One substance. So this one is homogeneous or homogeneous. All right. So in this case, and so one of the things I'm going to show you is you see how this is written as H2O plus that? That means they're still separate things, but they're in the same container. All right. So that's one way of also seeing a mixture. All right. Soil or dirt. Mixture. Hetero or homo? All right. Oxygen. Pure element. This one is trying to trick you, but pure air. It is a mixture. So even though I called it pure air, it's still a mixture of different things. It's a mixture of oxygen, nitrogen, and carbon dioxide. Now, that would be hetero or homo? Homo. Because look around here. Can I see the oxygen? Can I tell where, oh, there's a nitrogen molecule? Can I do that? No. So, all right. Iron. It's pure element. Sorry. I was trying to say element or compound, but I heard you say element as I said element. All right. So, again, that's not a complex skill that we have to do, but we should be able to recognize the difference in those. All right. Today we're going to get into material that leads into a little bit more math. So we are going to be doing temperature conversions between Kelvin, Celsius and Kelvin, or Kelvin to Celsius, either way. And then we will also be doing temperature conversions from Fahrenheit to Celsius. And I'm going to give you the formulas for those a little bit later. They're actually on there. It's just that it kind of wrapped around, so it's hard to see what it is. We're also going to start looking at energy, specifically the difference between a joule and a calorie, and being able to convert between those two. Those are both units of measure for energy. Or thermal energy is what we're going to be looking at in this class. So heat. And then we'll also look at law of conservation of energy and law of conservation of mass, both of those in today's lesson. All right, so law of conservation of mass. We've already kind of stated this one in chapter 1, so don't feel like you have to recopy it if you know it. All right, but law of conservation of matter basically says that all the matter that exists is not going to get any more. We're not going to get any less. It'll only change from one type of matter to another. All right, so there is no new matter. So you might have heard the statement for law of conservation of mass that matter is neither created or destroyed in a chemical reaction. Now, This is a little bit different because we're not creating new matter, but in a nuclear reaction, we can convert some matter into energy. All right. And vice versa. If we could create a fusion reaction on Earth, we're still producing energy, but by combining matter. So, yeah, it's been done as not in a controlled situation. It's been done as a warhead, as a bomb.
No, they actually do have a fusion reactor that's being worked on. It's a processes like stuff like that, but they did successfully launch it.
Not that I think you're going to find that's going to be they're falsifying things. They haven't been able to contain the heat because if that's the problem, and it would only work for small cycles. So and I watch that stuff. So um, um, so um, So nuclear reactions, both fission and fusion, they release a lot of energy and it converts matter and energy a little bit. And then in chemical reactions, however, the changes in mass are so minute that they can be ignored. So the only thing that happens in a chemical reaction is sometimes electrons are dissipated and things like that. But in nuclear reactions, there are slight changes in mass. All right. But in a physical and chemical reaction, the total amount of mass stays the same. So the big statement that I want you to have in a chemical reaction, we have an area that we call the reactants. And then the other side is going to be the products. So total mass here must equal the total mass here. So the total mass of the reactants must equal the total mass of the products in a chemical reaction. Everything that we do in this class. Okay. All right. So I'm going to present a chemical reaction and just kind of show you how some things are written on it. So here would be like a prompt of it. It says, so suppose we burn 58 grams of butane in a lighter. It will react with 208 grams of oxygen to form a certain number of grams of carbon dioxide and 90 grams of water. So looking at this, how we would show it in this class. All right. So we have butane plus oxygen, and that's 58 grams of butane, 208 grams of oxygen. So that's a total mass of 266 grams. And then we don't know how much carbon dioxide is produced, but we do know how much water is produced. So based on what I said about law of conservation of mass before, what should the total mass of the products be? 266. So those two things have to equal. Now, how do I find out the mass of carbon dioxide? I take 266 and subtract 90. So what would be the mass of carbon in this case? 176. All right. So in this, when you have to do these type of calculations, or when you have a law of conservation of mass question, it's basically wanting you to recognize that these two numbers have to be identical. However, these sets don't, but they have to equal the same thing. All right. So we've rearranged the order. So if we're looking at this chemically, butane is C3H. C3H8. Oxygen is O2. Carbon dioxide is CO2. And water is H2O. 3. So that's 6. 4 is 8. So that's 4. Plus 6 is 10. And so there's your balanced equation for showing that. So ultimately, I've rearranged how these molecules are arranged. Before, I had carbon attached to hydrogen. Oxygen was by itself. Oxygen, some of the oxygen attaches to carbon, some of it attaches to hydrogen, and it's created new compounds. That's why these numbers are different. All right. So we have to go on that based off of those things. All right. So every chemical reaction is driven by energy in some form. And the energy that we're going to look at in chemistry most of the time is going to be in the form of heat transfer. Some sort of heat energy transfer that is happening. All right. And so you might recall from middle school, or something like that, when you talked about what energy was, you might have gotten a definition that energy is the ability to do work. We can't, in the lab that we have, or really in any lab, you can't see one atom moving to another place. So we can't measure the distance traveled, really. So we have to measure the work being done in a different way. So we'll either measure the work being done by pressure produced and amount of gas production, things like that, or we'll measure heat transfer. How much heat energy has went from one place to another, and that's going to be the most effective way that we'll do it. So in the old definition of work from physical science or from physics, you'll see work is defined as force acting on a distance, or written as but we can't do that. We can't measure the force and the distance in chemistry. So we have to find another way. So what we look at, you'll see this popping up eventually, but delta H, change in heat. So we're going to look at how the heat energy changes. And so we have to measure that indirectly through looking at temperature. So we'll look at what goes up in temperature, what goes down in temperature. That says very recent. I hadn't read that. Net energy gain. Okay, so every time they've been losing energy for it. All right. So we talked about law of conservation of mass. There's also a law of conservation of energy. So theoretically, not theoretically, according to this law, all the energy that exists in the universe is constant. There's no change in the total amount of energy. It only changes form. So again, we can say that energy is neither created nor destroyed. However, it changes from one type to another. So the total amount of energy is constant. I wish I could use that. All right, so energy can be changed from one form to another, and energy can be transferred from one object to another. You've all seen that happen. If you've ever watched a pool game, the energy is transferred from one ball to the other ball. If you hit the cue ball into two other balls, that energy is not, there's no energy gain. The resulting movement from the other two, or if the cue ball continues moving, is going to be less than the original movement of just the cue ball by itself. So, but if they total them all up, it'll be equal to what the original was. Now, on Earth, we have to account for friction as well. All right, so unless we can create a totally frictionless environment, you're always going to have some, and I hate that we phrase it like this, you're always going to have some energy that is lost due to heat. It's not really lost because it's creating the heat. That energy is going there as well. So just kind of keep that in mind, that in any kind of collision reaction, any kind of energetic reaction, friction applies, so that friction has to be accounted for in your energy total as well. All right. So we look at energy in two ways: kinetic energy and potential energy. In this class, or let me ask it this way. In previous times, you've heard of kinetic energy. What is kinetic energy associated with? Motion. All right. Potential energy is usually referred to as, if I say that you have potential, the ability to, it's stored inside, it's kind of reserved. In this class, when we talk about kinetic energy, we're going to be talking about heat, because that's what we're going to watch move. Really, we're going to watch it transfer from one object to another. All right. For potential energy, that's going to be chemical energy stored in bonds. So when atoms and elements combine, chemical bonds, there's a certain amount of energy that's holding them together. Electrical energy is kind of in those bonds as well, because we can emit electrons and form electricity through chemical processes. So we have electrical energy, that's the energy associated with electrical charge. Thermal energy is going to be our kinetic. It's the energy associated with the random motion of atoms and molecules in matter. So that's kinetic. For some degree, that's potential, but it can also, once it's flowing, it's kinetic. So electrical can kind of be both. And then chemical energy. Chemical energy is going to be a potential energy that's associated with position of particles that compose a chemical system. So if I look at a molecule of water, all right, and I try to break down that water. The only way for me to do that in a lab, well, not the only way, but one of the ways I can do that in a lab is I can cause it to split into hydrogen and oxygen molecules. A simple way that you can do that is you take like salt water and you take electrodes connected to a battery, and really doesn't have to be a lot high voltage battery or anything like that. So if you take a glass of salt water, you drop a 9-volt battery in it, you're going to start noticing bubbles forming. One side, the positive side, you're going to notice a certain amount of bubbles. Positive side of the battery, you're going to notice a certain amount of bubbles forming. And then on the negative side, you're going to notice twice as many batteries forming. On the negative side of the battery, that's producing hydrogen gas. It's splitting the water molecules into hydrogen gas on that because hydrogen forms a positive ion, oxygen forms a negative ion. So there's twice as many hydrogens and oxygens. So you're going to produce that. I do see what you were talking about, Bill. I looked it up. They shut it down in January. Yeah. What they were talking about is there's no net gain of energy on it. Like they've done it, but they're taking more energy to do it than they're making. So in this, if I want to produce these chemicals, I have to split that some way. Now, the reverse of that happens in nature. The new water that's created on the planet happens during like volcanic eruptions. Anytime lightning strikes, new water molecules are created as well. Or not created, but formed. So we have to add energy to it to make that happen. But the energy added during a volcanic eruption actually gets stored in the bonds, and then when we split it, we release energy as well. So remember, like that hydrogen and oxygen, both of those things burn really, really well, so we can use those as potential fuel sources. So if you follow any kind of alternative fuel technology stuff, looking at future types of automobiles, one of the ones that's still promising, but again, it's expensive right now, is using hydrogen fuel cells in cars. All right, there's two different philosophies on it. One of them, you take the water, you split the molecules into hydrogen and oxygen, you use the hydrogen and oxygen as your fuel. That takes electrical current first. The other way is causing it to split where it produces electricity, and you run an electric car based off of that splitting. So one way runs on a traditional internal combustion engine, that you're burning the hydrogen, which is clean, or burning the oxygen, which is clean. The other way is using the water in a catalyst, and it splits it and it produces an electrical current as it's doing it, and then it runs an electric motor. Both of them are viable, but both of them have the same drawback. Neither one of them works well in the cold. And Toyota is probably on the forefront of it right now. I think they've released one in Japan and then released one model of it in California. But it's just because they have some issues with the engine. GM was working with it for a while, and they never could get it to where they could make a profit selling them. Is what it really comes down to, is when they can make a profit selling it. All right, so let's look at some units of energy. There are two main units of energy that we're going to use in this class. The first one is a joule. And then the second is called a calorie. Now, you've heard of calories before. Where do we usually associate calories? Food. The calorie that we associate with food is not this. The calorie we associate with food is 1,000 of those. So the calorie we associate with food is a kilocalorie or like you see it written on the packages, it's a capital C calorie. All right. So food calories represent 1,000 little calories. All right. So the related energy unit for nutrition, we use a capital C for the abbreviation, or we can say kilocalorie, KCAL, is equivalent to 1,000 little calories. So the little calorie is a heat calorie. And the actual way that we determine how much energy is in a piece of food is by burning that food and seeing how much the temperature change is. So they actually have something, it is called a bomb calorimeter, and you can take a piece of macaroni in it. It has like a little wire filament that we'll pass an electric current through, and that piece of macaroni or something is stuck to that wire. It catches it on fire, and we measure the heat change. We measure the temperature change, and that tells us how many calories there's in that piece of macaroni. We can do it with a piece of cake. We can do it with Diet Coke. We can do it with all of that. So there is real-world tests for finding out how much calories are in food. So they'll take, whenever they're trying to figure out how much energy is in a Burger King Whopper, they take a little piece of that Whopper and burn it, and then they calculate it for how much stuff is there. All right. And all of that. All right. So let's look at this a little bit more. Does everybody have what they need? All right, let's look at this a little bit more mathematically. So we're going to use conversion factors. So 1 calorie there is a relationship between calories and joules. 1 heat calorie is equal to 4.184 joules. So that's one conversion factor that I can use. And then 1 kilocalorie, so it can be written as capital CAL or KC like that, or KCAL, is equal to 1,000 calories. And I mean, this really isn't any different than what we've been doing. So if I looked at it in terms of this, I could also say that 1 kilocal is equal to 10 to the third CAL. And that's what we were doing in the last chapter. It's just recognizing how that conversion factor is produced. We can there is another unit that might pop up, but it's more of a unit of power than energy. It's a kilowatt, but we can convert kilowatts back into that. If that ever comes up, I'll give you the conversion that you need to use. I don't want to pull that one in because that we rarely ever see any problems with that. All right, or watts and things like that. All right, so how would we use this information? So I want to know how much energy in joules a candy bar, a Snickers bar, contains. So if I look at the package of a Snickers bar or something like that, I can see that it has 225 calories of nutritional energy. And I want to know, maybe I'm in physics or something like that, and I want to know how many joules that is. All right. So when we look at this, where the process that we're trying to go from, I'm trying to go from nutritional calories to joules. So I have to go through heat calories and then to joules. So what do I already know? I know that 1,000 heat calories equals 1 kilocalorie. We've already gotten that. All right. I also know that 4.184 joules equals 1 calorie. So I can use those as conversion factors. So I'm going from capital C calories to lowercase c calories. So I'm going to put, that should be a capital C on the bottom. You'll find a lot of times I'll write that as KCAL just because it makes more sense in my mind because it is actually a kilocalorie. All right, so 1 kilocalorie equals 1,000 heat calories. And then we also have, no, big C is a bigger unit. It means it equals 1,000 of the little c's. All right, so it's kind of like 1 kilometer is equal to 1,000 meters. A kilometer is larger than a meter. All right, it's the same thing with just a different end unit. All right, and then we can also use the relationship between heat calories and joules. So in this calculation, I'm going to multiply by 1,000, and then I'm going to multiply by 4.184. All right. So problem, we're given 225 kilocalories, and we're asked to find joules. So I'm going to start with my 225 kilocalories, and I'm going to use my conversion factor. All right. So at that point, now I'm in heat calories. So now I can go from heat calories to joules. And then I would multiply 225 times 1,000, and then times 4.184, and then how many sig figs can my answer be in? Or will my answer be in? So in this one, both of these are conversion factors. They're exact numbers, so they're not going to affect it. So that determines my sig figs. So my sig figs has to be 3. So both of the 1,000 to 1, that's a conversion factor, is considered exact. So it's not going to change my sig figs. Same thing with the calorie to joules. It's an exact number. So we know it's that. We know it to an infinite number of decimal places, so it doesn't affect it. So the one that's going to drive my sig figs in this one is my initial given. All right. Most of the time, the given will drive your answer. It's only only problems that it doesn't is with like density. Density, and then there'll be some where we do some calculations with change in temperature that it will, that something else in the problem will. So doing the math of this, I get 9.41 times 10 to the 5th, or if you did it in a calculator and you didn't have it in scientific notation, 941,000, something like that. All right. All right, so now you get an opportunity to try this on your own. I'll give y'all a minute to finish getting what you need. All right. So I want you, this time, instead of going from kilocalories to joules, this time we're going from kilojoules to calories. So I want you to go ahead and try to do this using the conversion factors that we have. So kilojoules to joules works the same way as kilocalories to calories. So 1 kilojoule equals 10 to the 3rd joules. And then we still have 1 calorie equals 4.184 joules. So go ahead, set it up, and see what you come up with. I've got it.
Kilojoule is 10 times 29, but 10 to 4. So it's 1,000. Wait, so then we have to divide it by 1,000. So then, kilojoule to joule. There will be more joules than kilojoules. Yeah. So we would move this way, the number would be bigger. Yeah, so kilojoules. So the number should be smaller. There's 1,000 joules and a kilojoule. Correct. So you multiply your kilojoule number by 1,000. That's your joule. I got it. Okay. I borrowed. Wait, 2%. Oh shit. Excuse me, you divide it. Yeah, it'd be but how many you say fake? One point.
Be a fun thing.
Yeah, 1.89 times. Yeah, I think that's 4. What do you mean? Did you multiply by 1,000 and divide it by 4.1? Right? Right?
All right. All right. Yes. 10 to the third. So kilo to base is always 10 to the third. Yes. Yes.
Okay, so we just did it backwards. We try to do calorie first.
Well, so
First, and then
so what you're actually doing here, this number, replace that with joule.
okay, so just put that here.
Put joule here.
1,000 joules?
Yeah, because 1 kilojoule is 1,000 joules. And then you're going to put joules on the bottom and calories on the top because that's what we're trying to go to. 184. Yeah.
So I was right.
All right. That is supposed to be a big C. And that's supposed to be a big C. All right. So, just kind of going our flow chart. I'm going from kilojoules to joules to calorie. So, my first step, I'm putting kilojoules on the bottom. So 1 kilojoule to 10 to the third joules. And then here, I'm going from joules to calories. So 1 calorie is 4.184. So now just kind of plugging in information. I have my given 4.51 kilojoules. That cancels that. Here, that cancels joules. And my answer is going to be in heat calories. All right. So I'm going to kind of point out one of the strategies I'm trying to show you. You'll notice a lot of times when I'm doing these type of problems, I map it out up here first. I try to predict where I'm going from and where I'm going to, and then I figure out the steps in between. So, here it tells us that we're going from kilojoules to calories. So I need to get from kilojoules to joules, and then I can go to calories. All right, so when we do this calculation, I'm multiplying by 10 to the third here first, and then I'm dividing by 4.184. So I'm expecting a large number. Can anybody tell me when we plug this into the calculator, what do we get? All right, 1077.9 something, right? All right, now, based on my given, how many sig figs can my answer be? 3. So I can only have 3 sig figs in my answer. So I can write it as 1080, and that tells me 3 sig figs. Or I can put this in scientific notation. It's 10 to the third, because I'm having to go 1, 2, 3 places. The decimal is assumed to be there. All right. All right. All right. So when we look at chemical reactions, there's 2 types of chemical reactions that we're going to do. One type of chemical reaction is exothermic. If it's exothermic, that means that energy is released. So energy goes from the reaction to the surroundings. All right. So if I'm releasing energy in a reaction, how are we going to experience that? As a elevated temperature or a decreased temperature? Elevated. All right. So in an exothermic reaction, the chemical reaction is going to cause whatever surrounding that reaction to heat up. All right. So if you remember the little whoosh bottle I did, that's an exothermic reaction. The bottle is hotter after the reaction than it was before it. All right. So we can look at this as in an energy diagram. You're not going to need to know these other than just recognizing what it's saying. So this is sometimes you'll see it's energy versus time. It's really energy versus progress of the reaction, because we can move backwards and forwards on progress. Like we don't always travel in a straight line on this. So if I have certain reactants, reactant A plus B, and I'm trying to show that this is a exothermic reaction, that means that reactants A and B up there have a lot of energy, and during the reaction, I'm going to lose it. So my product has less energy than the individual reactants did at the beginning. All right, so that means that this energy that we had up here went somewhere, so it exited. We had energy that went out into the surroundings. All right, so the surroundings gain heat energy. All right, So we look at it as a positive heat energy because we've lost it or it's in the product. All right. Now, the other side is an endothermic reaction. So in an endothermic reaction, energy is taken in or absorbed. All right. And the words almost kind of tell you what the heat is doing. Exo is exiting, endo is entering. All right. And so when we look at this, an endothermic reaction, when we look at the energy versus progress, the reaction. So this time, we're starting with our reactants. Notice that they're low on the energy ladder. And then in order to get to the products, the path that they're going to take, energy has to be added to it because now our product has more energy than our reactants. So that energy had to come from somewhere. So our heat energy is removed from the surroundings this time, so the heat energy goes in. All right, so surroundings lost heat energy is gained here. All right. Now, it's not really lost, it's just moved from one place to another. So, chemical reactions where you might see this. So, how many of y'all have ever had those little, like when you go camping, you know, those little packets, the hot hands that you stick in your pockets? That one's an exothermic. So, that one's giving off heat. If you've ever had an injury and you had one of those ice packs that you pop the little capsule on the inside, it feels cold to us, but what it's actually doing is drawing heat away from us into the reaction to cause the reaction to happen, or heat from the outside. So you feel that as cooler. If you take physics and if you take high-level physics, what you'll learn is cold doesn't really exist. It's just heat being removed from where you're at. All right, it's just the absence of heat. All right, so everything is about heat flow. Heat will always travel from an area of high concentration to low. So if somewhere is warmer, that heat's going to transfer to whatever's cooler. And it's going to reach a point of equilibrium where either they're both the same temperature, or if you're constantly adding energy on this side, it's going to heat the other thing up and maintain that. So now, again, and I've said this multiple times today, the atoms and molecules that compose matter, we know they're in motion. They're always moving. They're either, even as a solid, they're vibrating. So there's a certain amount of thermal energy in that desk right in front of you, even though it's a solid. If I want to make the desk warmer, I have to make the particles vibrate faster. So I have to add energy to it somehow. So we refer to that motion of particles as the inherent thermal energy. The more mass you have, the more thermal potential you have. Temperature, the temperature of a substance is an indirect measurement of that thermal energy. So it's kind of like the average amount of thermal energy present. All right. So temperature is not actually thermal energy. It's just telling you how much thermal energy something might have. So it's like an average of all the particles moving and things like that. And so thermal energy, which is also called heat, is going to be is the transfer or exchange of thermal energy caused by a temperature difference. So, when we contrast heat and temperature, so heat is the transfer or exchange of thermal energy caused by a temperature difference. And then temperature is a measure of the thermal energy of matter. It's not the measure of the exchange. All right. However, heat is the actual exchange where it's moving from one place to another. So heat So what all of this ultimately says is that heat energy will flow from a high temperature to a low temperature. And think about it like this. You stick a piece of metal on the stove or in a fire. The part of the metal that's in the fire is getting hotter. That heat energy is traveling up that metal rod, and then you go to grab that metal rod a little bit later. That heat is then transferred to your hand. All right, so it's always going to move from the highest heat source to the lowest in the area. Or you light the fire, you're sitting 3 feet away from it, you can still feel the heat coming to you because that heat energy is leaving the heat source and coming to you. All right. So just kind of we're going to look at the last thing we're going to look at is temperature conversions. I'm going to end up giving you some practice on this, but we may not get all the way through it today. All right. So the first thing I want us to look at is the Celsius scale. In Celsius, water freezes at 0 degrees Celsius. All right. In this class, the primary method of measuring temperature that we'll use is Celsius. All right. We will most of the time then convert it to Kelvin, but Kelvin's an easy conversion. All right. So water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. Now, that also means that ice will melt at 0 degrees Celsius and water will condense at 100 degrees Celsius. Just depends on which way the energy is traveling. All right. This classroom, typically room temperature is around 72, 73. So when we say room temperature is 22 degrees Celsius, we're referring to 72, 73 Fahrenheit. All right. 70 degrees, we're more like 19, 20 degrees Celsius, somewhere around there. All right. So the other scale that we will use in this class is the Kelvin scale. On the Kelvin scale, water freezes at 273 Kelvin and water boils at 373 Kelvin. So if I were to give you room temperature in Kelvin, we would be saying 295 Kelvin. And that would freak a lot of people out because 295 sounds like it's really hot. You know, if you understand it, it doesn't bother you. So I like to watch a lot of sci-fi stuff and all of that. One of the sci-fi movies, my favorite movie, is Pitch Black. And they go on a prison planet that the sun's hitting it and all of that. And the first time I watched it, I wasn't really paying attention. They were reporting the temperatures in Kelvin, but they just were saying numbers. So I was trying to figure out how, like, the first time I heard it, I'm like, man, that's, it's supposed to be really, really hot. And then I did the calculation, and they were looking at more like what we would call about basically Arizona temperatures in the summer. All right, that is really hot, but it wouldn't kill you hot like they were showing on the movie. So just be aware of that. And I'll say this, I don't want to have to turn on GoGuardian to see what people are doing on their screens behind it. Just make sure you're doing appropriate things on there, and not other people's work and watching videos and things like that. All right, so the whole point of the Kelvin scale is to avoid a negative number. All right, so a lot of the math that we do with temperatures, we don't really want negative numbers because we're going to be multiplying and dividing by zero, and are multiplying by zero sometimes, and a negative number messes up calculations in that. So we have to start with only positive numbers and numbers greater than zero. So absolute zero is 0 degrees Kelvin. That is the theoretical coldest temperature possible where all molecular motion stops. If you want to go down a rabbit hole sometime, you can look up YouTube videos and things of what would happen if we ever reached absolute zero. Some people go the worst case scenario that all matter stops in the universe because, you know, once you hit it in one place, it's going to expand. The other ones are just, you know, the energy required to reach that point would be so great, it's just not feasible, like economically feasible. There are some things that gets really, really close. If you look up the freezing point of of liquid nitrogen and our nitrogen, it's really, really low. The point where we get nitrogen to a solid. Now, we don't use it by dropping the temperature. We do it by increasing pressure. So there's other ways to manipulate that. Kelvin and Celsius, so if I'm looking at this, if I'm at 0 degrees Celsius, I'm at 273 Kelvin. So if I go up to 1 degree Celsius, I'm at 274. They're the same unit, it's just the scale has been shifted so that we don't have negative numbers anymore. So I'm gonna address Fahrenheit in a minute. All right. So the whole point of this is if I go to 0 Kelvin, I'm at negative 273 Celsius. Exact negative 273.15 if you want to get super specific on it. But I'm at negative 273 Kelvin. All right. So if we're going to compare all three temperature scales at the same time, I'm just using boiling point, freezing point, and all of that. So looking at Celsius, 100 degrees Celsius, 373.15 Kelvin, 212 Fahrenheit. 0 degrees Celsius is freezing point, 32 degrees Fahrenheit, 273.15 Kelvin. And then we come all the way down here. If we were using Fahrenheit scale, looking at the freezing point is negative 459.7 Fahrenheit is negative 273.15. And then we get absolute 0 Kelvin is that same temperature. All right. So again, this point is kind of a theoretical point. Nothing gets this low, but we can get really, really close to it. And so that's just kind of so you can see the comparison. This image is just a Google image. You can find that one and relate it if you want it. You'll see it a lot I'll put it on a lot of the worksheets that I give you for temperature stuff. I'll put it, it might even be on like the test that I create, just kind of so that you can visualize things. All right, so now, how do we get from one to the other? Here's what I'm going to give you. So if you're given information in Fahrenheit and we need to convert to Celsius, Celsius equals Fahrenheit, degrees Fahrenheit minus 32 divided by 1.8. So you could also write that. Let me put it somewhere where I know it's not going to affect us. So I could say, I could also write it like that. All right, just if it helps you see it that way. All right, now going from Celsius to Kelvin is pretty easy. So Kelvin is equal to Celsius plus 273.15. Pay attention to what your original temperature is written in. So if your original temperature is to the ones place, your answer is going to be to the ones place. All right, in any of these conversions. So sig figs matter in this, but they're treated a little bit differently. It's just whatever your original temperature is in, your new temperature is going to be to that place. Like we're not going to go to a greater degree of accuracy. All right. Now, so when we look at this, I give you these two. Your periodic table reference packet will have both of these formulas in there. What happens? What happens if we have to convert to Fahrenheit?
It goes up.
How do I use that formula to convert to Fahrenheit? Or which formula am I going to use? I'm going to use the one that has Celsius and Fahrenheit in it. But what I have to do is manipulate it so that I can get Fahrenheit by itself. So the first thing that I could say is degrees Celsius times 1.8 equals degrees Fahrenheit minus 32. And then degrees Fahrenheit is equal to degrees Celsius times 1.8 plus 32. And so we just flip it around. Fahrenheit equals degrees Celsius times 1.8 plus 32. So you should be able to manipulate that equation to get there if you have to. All right. I would know how to do it at the very least. There are probably going to be an instance where you're asked to calculate something that's given to you in Celsius and you have to know it in Fahrenheit. It'll only be in this chapter, but you will have to do it. Probably, yeah. I would write the Celsius one, the Fahrenheit one, and the Kelvin one. The Celsius and Kelvin you're going to have in your packet. The Fahrenheit you're not. So that's what I'm saying. You need to know how to get to Fahrenheit if you have to.